how it's two things being connected, right? We talked about like time and distance being related, and that's a relationship, or X and Y. That's the biggest thing we did, right? X and Y being related, and we related them with all different kinds of ways. We did graphs, mapping diagrams, ordered pairs, equations. We had all these different ways of relating two things. We're just going to review all the different things that we did do, or just remind ourselves what they are. So we relate things in words. That rarely ever happens, but sometimes it does. Okay. The first one we looked at, I believe, was table of values. So a table of values is the thing that looks kind of like this. You got like an X, you have a Y, and it's just table it. 1, 2, and 2, 4. Right? That's a table of values. So we'll call that a 9 maybe. Right? That's a table of values. It relates X's and Y's. We also talked about inputs and outputs. Right? So when you're looking at a table of values, your input is the first thing, your output is the second thing. Input being X, output being Y, like 99% of the time. We also talked about ordered pairs. Ordered pairs always look like this, where the X coordinate goes first, the Y coordinate goes second. Again, input is the first one, output is the second. The next way we connected things was with mapping diagrams. And mapping diagrams were a little tricky because we don't use them very often. A mapping diagram is where you have like the two bubbles. You have like 1, 2, and then 3, 4. And you had arrows coming out of one bubble and into the other. Like that. So that would mean 1, 3 is a point, 1, 4 is a point, and 2, 4 is a point. Because that's just how the arrows are pointing. Whichever side has the arrows coming out of it is X. Whatever side has the arrow coming into it is Y. So my inputs are the left one for this one, outputs are the right one. That was called a mapping diagram. The most popular thing we've seen recently is an equation. Equations always have something isolated, right, by itself. Typically, it's something like y equals. Right? We say y is isolated, it's by itself. And then you have some sort of numbers and letter combination. We're going to say 2x plus 4. Whichever variable is isolated by itself, that's our output. Whichever one is connected to all the numbers, that's our input. That way we could input a number and get an output by calculating. Right? Just putting that all in our calculator. And the very last one that we did, which we have seen a lot of, is a graph where we have x's go left to right, y's go up and down. Again, x is the input, y is the output. Fantastic. We called everything a relation. So anything that connects two pieces of data or two quantities is called a relation. A special type of relation is called a function. Right? That's what we're going to do today. We're going to define something called a function. Functions are relations. They're just special relations. Awesome. I don't know if we really need to look at this. Yeah, we'll look at it, I guess. As well. Alright. So, we've got these two different mapping diagrams here. They're both relations, right? They're connecting data. The first one says is a multiple of, and the second one said is a square of. So, for instance, like 1 is a multiple of 1. 4 is a multiple of 2. 4 is also a multiple of 1. And that kind of makes sense? So if I look at 9, 9 is a multiple of 3. And 9 is also a multiple of 1. And 3 times 3 would be 9. 3 or 9 times 1 would be 9. So that would work too. I guess we missed an arrow here. 4 is also a multiple of 4. And 4 times 1 would be 4. And then 16. 16 is a multiple of 4. 4 times 4. 16 is a multiple of 2, 2 times 8. And 16 is a multiple of what? 16 times 1. These numbers on the left can be connected to these numbers on the right, assuming that the arrows mean is a multiple of. My inputs in this case would be here. Input. My outputs would be here. The reason being, the arrows are going that way. Awesome. If you look at number 2, it says is the square of. So, for instance, 1 is the square of 1. So if you did 1 squared, it would equal 1. 4 is the square of 2. 2 squared equals 4. That means 9 is the square of 3. 3 squared would equal 9. 16 is the square of 4. 4 squared is 16. Again, looking at those, because the arrows go from left to right, the input is here, the output is here. Just for definition's sake from the beginning of the unit, in case we forgot that. Fantastic. We're going to take that data and we're going to write it as order of pairs. Okay, so we have these things here. We're going to write them out as order of pairs. The first one's going to have quite a few. So we have 1, 1 is an ordered pair. 4, 1 is an ordered pair. 4, 2 is an ordered pair. 4, 4 is an ordered pair. Right, I'm just looking at these inputs, figuring out where the arrow goes, then turning it into an ordered pair. That means if I look at 9, 9, 1 would be an ordered pair. So I have an arrow going from 9 to 1. Also, 9, 9 would be an ordered pair. Right, 9, oh sorry, we didn't have 9, 9, we had 9, 3 though. 9, 3 would be an ordered pair. Arrow went from 9 to 3. For the bottom number, if we look at 16, we have 16, 1. That's an ordered pair. I have 16, 2 as an ordered pair. And I have 16, 4. Fantastic. Look at the second set of ordered pairs, and we want to write these things all out. It's not going to be quite as many. Right? The first input is 1. It only has 1 arrow coming out of it. It goes to 1. So 1, 1 is one of my ordered pairs. My second ordered pair, the number 4 is an input. It has an arrow going to 2, which is an output. So 4, 2. Number 3, my input of 9 has an output going to 3, so we have 9, 3. And the last one is 16, 4. So we've taken those mapping diagrams, we've written them as ordered pairs. Awesome. Just a reminder, you could graph these ordered pairs. We're going to try, just kind of roughly. So if you're looking at this, inputs are across the bottom, outputs are along the top. So if I wanted to graph these ordered pairs, I would have 1, 1 right there. I'd have 1, 4 right there. 4, 2, 4, 4, 9, 1, 9, 3, 16, 1, 16, 2, and 16, 4. Right, that's how that graph would look. That's me putting all the ordered pairs, inputs along the bottom, outputs along the top. X's, Y's. They've put domain and range, which we're going to talk about in a little bit. Don't sweat it right now if you forget what that means. Looking at the second graph, I can take those ordered pairs. I have 1, 1, 4, 2, 9, 3, and 16, 4. Beautiful. That's like all the types of data we basically remember doing, except for we didn't have equations or a table of values in those equations. Fantastic. To this point, we discussed all these things as being relations. It's connecting two pieces of data. So it's a relation. One of these relationships is actually a special relation called a function. And we're going to explore that idea. The other one is not a function. Okay, the definition of a function is right here at the top of page 456. It says each element of the of the domains is related to exactly one element of the range. That's the definition of it. All right. In layman's terms, like in regular people speak, instead of saying that, I would say that every one output, or every output, every input only has one output. That's what makes a relation a function, if it follows this rule. So every input has exactly one output. What that means, if I say, hey, the input's 2, you should be able to look at your thing and be like, that means the output is 6. It doesn't mean the output could be 6 or 3 or 1. And looking up at our previous question, if I said, hey, the input is 4, looking at the first question, your output could be 1 or 2 or 4. That's 3 different outputs for one input. This thing is not a function because it doesn't follow our rule. This thing is a function because every input has one output. If I say, all right, the input is 4, you know what the output is. It's 2. There's no debate. It's the only output that comes with it. If this thing's a function, this thing's not a function. Because of how the inputs and the outputs relate to each other. In a mapping diagram, it's not so bad, right? You can kind of visualize it. Oh, that input's got too many outputs. That doesn't work. On an ordered pairs, what you're looking for is if you're going to repeat any inputs. So again, if I say, all right, the input is 9. Looking at these ordered pairs, knowing the input is 9 means I'm either this one or this one. There's 2 different outputs. On the other question, if I say, hey, the input's 9, you should know, oh, then the output's 3. Not a function, is a function. This one has repeated x values. This one does not. For the graph, we can do the same thing. I say, hey, your input is 1. So I look at 1. Oh, look, I have 2 different outputs that have inputs of 1. This graph, I say, hey, your input's 16. You know, 16, there's only 1 output. And that works for every single point on that graph. Graphs are special. We're going to learn something called the vertical line test in just a little bit. That'll handle graphs for us. Okay. Biggest thing, a function. Every input only has 1 output. In math, that means there's no repeated x values. We just discussed kind of this stuff right here. So for an arrow diagram, a mapping diagram. Okay, so for a mapping diagram, explain how we can determine which relation is a function by looking at the following: the arrow diagram. I'm going to say mapping diagram because I'm going to keep calling it arrow diagram if I keep looking at it like that. Mapping. In words, how can I check if a mapping diagram is a function? I'm going to look at the inputs. look at inputs. That means the arrow's coming out. None of them that was crazy. None of them can have more than one arrow. And I'm going to just say leaving it. Just in case you forget what the input is, inputs have the arrows leaving it. So if I get a mapping diagram, I look at my inputs. If any of them have more than one arrow, not a function. Automatically not a function. You could have 99 of them all with one arrow, and the last one has 2 arrows, the whole thing is not a function. Okay? Every single input has to follow my rule. Awesome. For B, ordered pairs. When looking at an ordered pair, you can have no repeated x values. Remember, in an ordered pair, x is the first one, y is the second one. So if you're looking at a big set of ordered pairs, and you notice that, hey, this ordered pair has an x value of 2, this ordered pair has an x value of 2, not a function. They've repeated an x value. The y's can do whatever they want. Right? Y's can repeat, they can do whatever they want. The x's cannot. C for graphs, we're going to say passes the vertical line test. Vertical line test. For short, we call this the VLT. And I believe at the top of your next page, there's an explanation of what VLT is. I'm about to explain it right now so you can see what a VLT is. I've never done VLT on this, so we'll see how it works. On a smart board with like our old notes, it was really easy to kind of visualize it. So it's going to be a little trickier this time. So we'll figure it out. If I have an equation, I would turn it into a graph to check to see if it follows the VLT. Okay, so if I have something, you can always turn it into a graph and then do your VLT, which is what a lot of people do. Right. Just real quick. All right, class example 2. Each of the following is the graph of a relation. We're going to answer right at the bottom, there's like a little chart in the bottom right-hand corner. We're going to do true or false for those things. So it says, I'm trying to get the whole thing. For the following statement, it says true or false. Number 1, for each input value, there's only one output value. Yeah. Looking at graph A. For every input, there's only one output. Inputs are your x values, right? Left and right. Outputs are your y values, up and down. If I look at this graph and I say your input is -2, I look over here at -2, and I try to see if I know the output. The output for -2 would be up here at 4, and there's only one output. Right? There's no multiples. There's nowhere else on the graph I get an output when I have an input of -2. If I keep looking along, I'm like, okay, what about like -3? How many outputs are there for -3? If I look at -3 and I try to figure out where the output is up here. There's only one of them. There's nowhere else on this graph that I have an output for -3. Just that one spot. This thing has only one output for every input. That is true. If you look at graph C, we're going to skip B for a second. And I said, okay, does every input have only one output? I look at, say, my input of 1. I say, okay, give an input of 1. What's the output? There's technically 2 outputs for this one. There's an output here at about 2, and there's an output here at about -2. See how there's 2 different outputs for that input. For example, we do another one. Let's do -2. Input's -2. There's 2 spots on this graph where x equals -2. Right there and right there. This graph is an example of not having only one output for every input. So this would be false. Looking at B, every input would only have one output, not multiple spots, right? So B would be true. And D would be false. Looking at D, if I chose an input value of 5, I notice I could go up and hit the graph or go down and hit the graph. Right? There's 2 outputs for that input. So that would be false. For question 2, for each output value, there's only one input value. We're just going to scratch this because you don't even need to know it. And it's just going to muddy the waters for people. Part C. The relation is a function. A function has only one output for every input. So if you're looking at this, that means graph 1, since the first part was true, it is a function. So that is true. It only had one output for every input. That means number 2 is also a function. Number 3, or C, was not. Number 4, C, was not. That's the math behind if something's a function or not. Okay, you check input values. You try to notice if there's an output value or more than one output value. The practical way to do it is something called the vertical line test. So how the vertical line test works, it's going to be tricky. Can I use a ruler? It says you take a vertical line to a graph. I'm going to take a ruler. Vertical line. I'm going to hold it straight up and down. You could use your pencil if you want. If you run a vertical line across your graph, it should never touch your graph at more than one spot. So for instance, if I take this and I put it right here, you'll notice that it's touching my line only at one spot, right there. Maybe this, let's try to see through it. No. A little better, a little better. It's touching the graph at one spot, it's touching right here. If I move this ruler across, it's still only ever touching the graph at one spot. That spot is just changing, right? It's going all the way across like that. This ruler, when it's vertical, could never be touching the graph at 2 spots. That's called passing the vertical line test. When you fail the vertical line test, is if you can take a straight line or a straight object, put it on your graph, and touch it at 2 spots at the same time. So notice how I have this vertical line. It's on my graph. I'm touching once there, once there. This fails the vertical line test. Therefore, it is not a function. It's a really quick way to be able to check if a graph is a function. You just take a vertical line, run it across. Never touches more than once, you're good. If at any point it touches more than once, no good. That means for B, I run a vertical line across it. You'll notice I'm touching here, and as I move across, I'm always only touching at one spot. For D, I take my straight edge, start here, I'm only touching it one spot, and then all of a sudden, look, I'm touching it two spots. Two spots. Two spots. This fails the vertical line test and would not be a function. I believe the next page has an explanation in words for you. Yeah, vertical line test. There you go. The vertical line test can be used on a graph of a relation to determine whether the relation is a function or not. If every vertical line drawn on the domain, that's the x values, intersects the graph exactly once, the relation is a function. So the vertical line only touches once, at all moments. If any vertical line touches the graph more than once, it is not a function. It's still a relation, just not a function. Fantastic. We're going to do a couple questions just to finish off this lesson. We're going to look at some pieces of data, some relations, and we're going to decide which ones are functions, and we're going to explain our answers. Okay, we're going to justify it. So you look at A. It says determine which of the following are functions. These are ordered pairs. To check if an ordered pair is a function, you check the x values. So I look at all my x values. We said functions can't repeat x values. I look. I never repeat the number 5. I do repeat the number 6. This thing is not a function. It has a repeated x. And like life lesson, you should like never repeat x. Okay? Why an x? Just let it go. Life advice. Number 2. Like 2 people laughed. I appreciate you 2 people. So if you look at question 2, you want to know if that thing is a function. It's ordered pairs, so you're going to check your x values. You got 3, 2, 4, -3. You never repeated any of your x values. Notice that you did repeat your y values. Right? 3 and 3. We don't care about that. We only care about x values when it comes to functions. This thing is a function. No repeated x. For C, we say, is this thing a function? This is a mapping diagram. What we said is for a mapping diagram, you look at your inputs. Okay, my inputs are these guys, inputs. And we said none of your inputs can have 2 arrows connected to it. If you look, A only has 1 arrow, B only has 1 arrow, C only has 1 arrow. This thing is a function. Reason why? No input has more than 1 arrow. You can have inputs with 0 arrows and it still counts. Right? It just can't have more than 1 arrow. That's the definition of a function. If you look at D, we have a graph. The best way to check a graph is by using the vertical line test. If I can draw a vertical line that touches the graph at 2 spots, it's not a function. Looking at this thing, there's my vertical line. I am touching the graph at 2 spots. This fails the VLT. It is not a function. And we just say as our justification, failed VLT. Everywhere else it passes the VLT. That's the only spot it failed it. Awesome. E, the relation connecting the provinces and territories to their capital cities. Okay, so your input is your province. Your output is your capital city. If I name a province, Alberta, and you connect it to its capital city, Edmonton, damn it, got my geography down. Would I ever have a repeat? So for instance, if I give you an input, if I give you Alberta, would you ever have 2 outputs? Would you ever say, oh yeah, that's got 2 different capital cities? Probably not. Would you ever go the other way? Would I ever say, here's a capital city, and it's got 2 input values? Right? No, it's never going to happen. Those things are always just 1 for 1. Right? Input, Alberta, output, Edmonton. Sometimes when we talk about this, I like to see if I can remember them all, because I usually can't. And that's probably bad. Like living in Canada, you should probably know them all. BC is Victoria. Okay? You guys are going to have to correct me here. Alberta's Edmonton. Saskatchewan's Regina. Manitoba's Winnipeg. Usually people who live there, like, those are my go-to people. Ontario is Toronto. Quebec is Montreal. Is it Quebec City?
Yeah.
Oh, I just failed all of us Quebec people. PEI is Charlottetown. Nova Scotia's Halifax. New Brunswick is St. John's.
No. Isn't it like
Fredericton. Newfoundland, St. John's. I should know that. St. John, Newfoundland. Not St. John, New Brunswick. Who would say that? My bad. St. John's or St. John?
It's St. John's and Newfoundland. St. John and Newfoundland.
Both?
There is a city.
Oh, there's a city in both. Oh, okay.
Fredericton's the capital, and St. John's the capital.
Oh, look at the things I'm learning. And then the ones I don't know are like Nunavut's Iqaluit?
Yep.
Yeah.
Oh. You know, Nunavut wasn't a thing when I was learning geography? Dating myself. It didn't exist. It was just the Northwest Territories. It was just one big thing. And then when I was in like grade 6 or something like that, they cut it in half. And they created 2. Yeah. The more you know. Northwest Territories, Whitehorse? No, that's Yukon. Yellowknife. Yellowknife. Yellowknife is Northwest Territories.
I have no clue.
Whitehorse is Yukon. Yeah. Yeah, one of those, right? And they have like less people than anything.
I'm pretty sure you still ask. I don't know.
My family's from PEI, so my aunt just visited, and they're having their provincial election too. And we were talking about like how many members of parliament they get, like MPs in PEI, because PEI's got a really small population. Like the whole island is less than Calgary, right? So actually, the whole island is probably pretty close to Red Deer. They get 3 members of parliament. So as she was talking about it, she's, I guess, way back in Confederation. Look, I was learning social studies on the weekend. Way back in Confederation, when they first like created the country, PEI was like, we're only going to be part of your country if we get 3 members of parliament, and we're always guaranteed 3 members of parliament. And so they agreed to that like 100 and something years ago, and it's just always stuck. So even though like Canada as a population has exploded, PEI has just like remained this little island with nobody on it, and they still get 3 members of parliament every year, no matter what. Isn't that funny? The more you know. PEI, they get too much say. Don't tell my family that. Oh, potato farmers, I'm all mad. This is a function. And it's a function because of that awful explanation I gave. if you ever get a question in words and you're not sure, write them as ordered pairs and then check to see if you ever repeat it next time. It'll help, right? So, like, for instance, when I say Alberta, I know I'm only going to have one ordered pair for Alberta. So we Alberta, Edmonton, right? The connection's going to be nice. Looking at F and G, we have graphs. That means we're going to try the vertical line test, right? If I take a vertical line across graph F, will I ever touch graph F twice? So if I'm looking, I run a vertical line across it, I'm always only touching once. You'll notice this graph always is moving towards the right. It never has any sort of repetition. This thing passes the VLT. It is a function. I'm going to scroll this up a little bit so you can see better. Passes VLT. If you look at G, could you draw a vertical line that touches that graph more than once? So if you start off, you couldn't. Then all of a sudden, you could. That's a vertical line. It actually touches once, twice, 3 times. This thing is not a function. It fails the VLT. For the record, all of those things are relations. Relations just means two things connected. Functions are things that have only one input for one output, or only one output for every input. Fantastic. The last thing we're going to do, we don't do functions as mapping, okay? So don't sweat this part. What we do want to do is just classroom example 4 and just part B. Okay, so I'm going to get rid of this. We don't do function mapping here. And we're also going to get rid of this. But I do just want to talk about domain and range a little bit. Okay. It says, consider the function 3x plus 1 for the domain -1, 0, 1, and 2. All we're going to do is question B. List the elements of the range of the function. So when people see these questions on tests or assignments, they kind of freak out. Like, I don't know what you're talking about. So you need to remember what domain and range mean. And remember, we did a whole lesson on it. Domain means X values. Range means Y values. What they've done in this question is they've given you an equation and they've given you X values. Or inputs, right? Inputs. Then they've said, using that equation, what are your Y values or your outputs? To calculate your outputs, you just use your inputs in the equation. So for instance, my first output would be Y equals 3. Instead of X, I go bracket -1 plus 1. I took this equation, I changed my input, my X, to be my value. Right, took that equation, changed my input value. Then I just calculate that. Okay, put this in your calculator. When you do, you're going to get an output value of -2. That's the first thing in my range, -2. Then I'm going to keep going. Okay, I've done one of my inputs. I have 3 more to go. I go back to my equation. I say Y equals 3. Instead of X, I put 0. That's my second input value. And I go plus 1. again, I put that in my calculator, I get y equals 1. That is now my second range value, or my second output. I keep going. I now have a third one. I have a third input value, positive 1. I go back to my equation. I go y equals 3 instead of x. I go bracket, bracket. And then I go plus 1. Again, I calculate it. I get y equals 4. My very last one, y equals 3, then bracket 2, plus 1, y equals 6. Nope, sorry, 7. My range for this question would be -2, 1, 4, 7. That would be my range. And remember, domain means here's your input values. Here's possible inputs. If I say, what's the range? Well, use your inputs to figure out your possible outputs, and that would be your range. All the other stuff on this page, like the mapping, don't worry about that. And don't sweat it. Fantastic. Anybody have any questions about that? Doing a range kind of comes up